When we think about ancient life, dinosaurs inevitably steal the spotlight. These magnificent creatures dominated our planet for over 160 million years. But here's the thing that might surprise you. They were relative newcomers to Earth's grand story. By the time the first dinosaur took its inaugural steps, our planet had already been hosting life for a staggering 3.2 billion years. Today, we're embarking on an epic journey through deep time, a voyage that will take us from Earth's violent birth to the moment when dinosaurs finally appeared on stage. This isn't just a story about ancient creatures, it's the story of how life itself learned to exist, adapt, and eventually thrive on the planet that was initially hostile to everything we recognize as living. So buckle up, because we're about to explore the most fascinating chapters in Earth's biography, the ones that set the stage for everything that followed. Our story begins 4.6 billion years ago, when our solar system was essentially a cosmic construction site. Picture this. The newly formed sun is surrounded by a swirling disk of dust, gas, and rocky debris. Within this chaotic maelstrom, countless collisions are taking place as particles stick together, forming larger and larger bodies. Earth emerged from this cosmic demolition derby through a process called accretion. Countless planetesimals, some the size of mountains, others as large as small moons, smashed together with incredible violence. Each impact added mass but also tremendous heat, turning our young planet into a molten hellscape. The early Earth was nothing like the blue marble we know today. Imagine a world shrouded in a thick, toxic atmosphere of methane, ammonia, and hydrogen sulfide. The surface was covered in seas of liquid rock, punctuated by towering volcanic eruptions that would make Mount Vesuvius look like a backyard campfire. Asteroid impacts were so frequent that the planet's surface was constantly being reshaped and remelted. This period, aptly named the Hadean Eon, lasted from Earth's formation until about 4 billion years ago. The name comes from Hades, the ancient Greek underworld. And trust me, if you could have visited Earth during this time, you'd understand why geologists chose that particular reference. But here's where the story gets interesting. Even in this seemingly impossible environment, the building blocks of life were slowly coming together. Around 4 billion years ago, something remarkable happened. Earth began to cool down. This wasn't a quick process. It took hundreds of millions of years for the planet to become hospitable enough for liquid water to exist on its surface. As the temperature dropped, water vapor in the atmosphere began to condense. What followed were torrential rains that lasted for millions of years. Imagine the longest rainy season in history, except it continued for longer than complex life has existed on Earth. These endless downpours gradually filled the low-lying areas, creating the first oceans. These primordial seas were nothing like today's oceans. They were rich in dissolved minerals and gases, creating a chemical soup that would have been toxic to most modern life forms. The water was likely greenish-brown, filled with iron, sulfur compounds, and other elements that had been leached from the cooling rocks. But within this seemingly inhospitable environment, chemistry was working its magic. The combination of heat, pressure, chemical diversity, and energy from lightning strikes and volcanic activity created the perfect laboratory for life's first experiments. Somewhere around 3.8 to 4 billion years ago, in the depths of these ancient oceans, the impossible happened. Life began. Now, I should be honest with you. We don't know exactly how this occurred. The origin of life remains one of science's greatest mysteries, and despite decades of research, we're still debating the details. What we do know is that the first living organisms were incredibly simple. Single-celled prokaryotes that lacked the complex internal structures we see in modern cells. These early life forms were anaerobic, meaning they didn't need oxygen to survive. In fact, oxygen would have been poisonous to them, which is ironic considering what was about to happen to Earth's atmosphere. These primitive organisms were remarkably hardy. They had to be, considering the hostile environment they inhabited. Some lived near volcanic vents on the ocean floor, others in shallow tidal pools that were constantly being stirred by impacts and volcanic activity. They obtained energy through chemosynthesis, breaking down chemicals in their environment rather than using sunlight. For nearly 1 billion years, these simple prokaryotes had Earth virtually to themselves. They slowly spread throughout the oceans, adapting to different environments and evolving new ways to extract energy from their surroundings. But then, around 3.5 billion years ago, something revolutionary happened that would change our planet forever. Enter the cyanobacteria, microscopic organisms that would become the most important life forms in Earth's history. The Great Oxygenation Event was triggered by cyanobacteria producing oxygen through photosynthesis, with some developing into multicellular forms as early as 2.3 billion years ago. Now, before you start applauding these tiny heroes, remember that their gift of oxygen was actually Earth's first major pollution crisis. The oxygen released by cyanobacteria steadily accumulated over vast swathes of the ocean and oxygenated the water, gradually escaping into the atmosphere where it reacted with methane. This process, known as the Great Oxygenation Event, began around 2.4 billion years ago and represented the planet's first mass extinction. The oxygen that we depend on today was essentially a toxic waste product that killed off most of the existing anaerobic life forms. It's somewhat darkly amusing that the very gas we can't live without was once considered a lethal pollutant. But evolution is remarkably adaptable. Some organisms learn to not just tolerate oxygen, but to use it for energy production through aerobic respiration, a process that's far more efficient than anaerobic metabolism. This gave oxygen-breathing organisms a significant advantage, setting the stage for the development of more complex life forms. The oxygenation of Earth's atmosphere also had other profound effects. Oxygen in the upper atmosphere formed the ozone layer, which began protecting the planet's surface from harmful ultraviolet radiation. This would eventually make it possible for life to venture onto land, but that's still billions of years in our future. What followed the Great Oxygenation Event was a period that paleontologists sometimes call the boring billion, though I prefer to think of it as the patient billion, from about 1.8 billion to 800 million years ago. Life on Earth appeared to be in a holding pattern. During this time, the first eukaryotic cells evolved, cells with nuclei and other internal structures that are the building blocks of all complex life. This was actually a monumental development, even though it happened very slowly. The evolution of eukaryotes involved one of the most important partnerships in the history of life: endosymbiosis. Picture this. Larger cells began engulfing smaller ones, but instead of digesting them, they formed a mutually beneficial relationship. The smaller cells became specialized organelles like mitochondria and chloroplasts, while the larger cells provided protection and resources. It's like the ultimate roommate arrangement, one that has been working successfully for over 1 billion years. But despite these crucial developments, visible life remained frustratingly simple. The fossil record from this period is sparse, consisting mainly of microscopic organisms and simple multicellular structures. Earth's oceans were populated, but if you could have snorkeled through them, you wouldn't have seen much that looked like what we consider life today, then around 635 million years ago. Something extraordinary began to happen. The organisms of the Ediacaran period first appeared around 600 million years ago and flourished until the cusp of the Cambrian 538.8 million years ago. This period, named after the Ediacaran Hills in South Australia where their fossils were first discovered, introduced us to Earth's first experiments with complex multicellular life. The Ediacaran period was officially ratified in 2004 by the International Union of Geological Sciences, making it the first new geological period declared in 120 years. And for good reason. The Ediacaran biota represents a crucial chapter that was largely missing from our understanding of early life. The Ediacaran organisms were unlike anything that came before or after. These soft-bodied organisms were preserved as fossil impressions in sandstone, with evidence found as impressions of blob-like animals or more symmetrical forms reminiscent of modern jellyfish, worms, and sponges. Some of these creatures were truly bizarre. Take Dickinsonia, an oval-shaped organism that could grow up to 1 meter in length. It had a quilted appearance with segments running down its body, but no obvious head, tail, or mouth. How it fed remains a mystery. Some scientists think it absorbed nutrients directly through its skin. Then there was Charnia, which looked like a fern frond but was actually an animal. It lived attached to the seafloor, swaying in the ancient currents like an underwater plant. These organisms represent evolution's first attempts at building large, complex bodies, and while they were ultimately unsuccessful, they paved the way for what was to come. The Ediacaran world was peaceful in a way that Earth would never be again. There were no predators, no shells, no teeth, just strange, soft-bodied creatures quietly going about their business in the planet's first multicellular communities. Then, approximately 541 million years ago, life hit the accelerator. The Cambrian Explosion wasn't really an explosion in the traditional sense. It unfolded over tens of millions of years. But in geological terms, it was like someone had suddenly turned on all the lights in a previously dark room. What makes the Cambrian Explosion so remarkable isn't just the diversity of new life forms that appeared, but the speed at which they evolved in a relatively short period of geological time. Life invented almost every major body plan that we see in animals today. Eyes, shells, claws, complex nervous systems, segmented bodies, all of these innovations appeared during the Cambrian. The trilobites were perhaps the most successful of these early experiments. These arthropods, with their distinctive segmented bodies and complex compound eyes, became the dominant marine creatures of their time. Some species developed elaborate spines and decorative features that would make a medieval knight jealous. They were the first organisms to develop sophisticated vision, with some species having eyes containing over 15,000 individual lenses. But the Cambrian seas were also home to some truly alien-looking creatures. Anomalocaris, whose name means strange shrimp, was the apex predator of its time. Growing up to 2 meters long, it swam through the water using undulating fins along its sides, grasping prey with its flexible front appendages that looked like nothing so much as a pair of elephant trunks. Then there was Hallucigenia, an animal so bizarre that paleontologists initially reconstructed it upside down and backwards, with its spiny back and tentacle-like legs. It looked like something from a fever dream. The fact that we initially got its anatomy completely wrong tells you something about how different these early animals were from anything alive today. The Cambrian Explosion raises fascinating questions that scientists are still trying to answer. What triggered this sudden burst of evolutionary innovation? Was it rising oxygen levels, the evolution of predation, changes in ocean chemistry? The answer is probably all of the above, working together in a complex feedback loop. One thing is certain, the Cambrian established the arms race between predators and prey that has driven evolution ever since. Once animals started eating each other, there was no going back to the peaceful Ediacaran world. Following the Cambrian, the Ordovician period, 485–444 million years ago, saw life consolidating and expanding on the innovations of the previous era. This was the age of the Great Ordovician Biodiversification Event, a period of sustained evolutionary innovation that tripled the diversity of marine life. The Ordovician seas were dominated by massive cephalopods called nautiloids, some of which grew to impressive sizes. Cambrian, with its straight cone-shaped shell, could reach lengths of up to 9 meters. Imagine a giant ice cream cone with tentacles, and you're getting close to the right mental image. But perhaps the most impressive predators of the Ordovician were the Eurypterids, or sea scorpions. These weren't true scorpions, but they were definitely intimidating. Pentacopterus, one of the earliest known species, could grow to over 1.7 meters in length. With their powerful claws and intimidating appearance, they were the stuff of nightmares for smaller marine creatures. During this time, the first vertebrates were also making their mark. Early jawless fish like Sacabambaspis swam through the Ordovician seas, their bodies covered in heavy armor plating. They may not have looked like much, but they represent our own distant ancestors, the first creatures with backbones. The Ordovician also saw the first tentative steps of life onto land. Simple plants, probably similar to modern liverworts and mosses, began to colonize the margins between land and sea. These pioneer species were taking on one of evolution's greatest challenges, learning to live without the support and protection of water. All good things must come to an end, and the Ordovician's flourishing biodiversity was brought to a crashing halt by one of the most severe extinction events in Earth's history. Around 444 million years ago, a devastating ice age gripped the planet. This wasn't just any ice age. It was a global deep freeze that locked up massive amounts of water in polar ice sheets, causing sea levels to drop dramatically. The shallow seas that had been the cradle of Ordovician diversity suddenly vanished, taking their ecosystems with them. The numbers are staggering. Approximately 85% of all marine species went extinct. The great nautiloids were decimated, along with many trilobite species and countless other marine creatures. It was a harsh reminder that even the most successful organisms are vulnerable to planetary-scale changes. Ironically, this catastrophe may have been triggered by the success of early land plants. As these pioneers spread across the continents, they began absorbing carbon dioxide from the atmosphere through photosynthesis. This reduced the greenhouse effect, leading to global cooling and the onset of the Ice Age. It's a sobering example of how life can inadvertently engineer its own downfall, something that feels remarkably relevant to our current situation. By the end of the Ordovician extinction, Earth had been hosting complex life for nearly 100 million years. The planet had already witnessed the rise and fall of entire ecosystems, the evolution of predation, the development of complex body plans, and the first tentative colonization of land. When we think about the age of dinosaurs, we're really thinking about just the final act of a much longer play. By the time the first dinosaurs appeared in the late Triassic, around 230 million years ago, life had already written most of the fundamental rules that would govern complex ecosystems. The story we've traced today, from the first prokaryotes to the Cambrian Explosion to the Great Ordovician diversification, represents the foundation upon which all subsequent life would build. Every major innovation we see in modern ecosystems has its roots in these ancient seas. Predation and defense, complex body plans, sophisticated sensory systems, and the endless evolutionary arms race between species. Next time you see a dinosaur skeleton in a museum, remember, these magnificent creatures were standing on the shoulders of giants, tiny, microscopic giants that spent billions of years learning how to live, evolve, and thrive on a planet that never stopped changing. The story of life before the dinosaurs isn't just prologue, it's the main event. And as we'll see in our next episode, the lessons learned in these ancient oceans would prove crucial when life finally decided to conquer the land.